Recording is rolling. It is Tuesday, January 27. We're going to pick up from yesterday with this pendulum lab. Yesterday, you guys gathered the data. Today, we're going to do graphs and conclusion. Guys, don't worry about anything that says AP because you guys are honors. So we get rid of anything that says AP, just to scratch out. Right. And then we'll probably have some time to get in class, about 15 minutes. I'll start on, in general, simple harmonic motion notes. Harmonic motion, you think of this oscillatory motion, like has a time period and the cycle associated with it. Right? There's some other scenarios. The pendulum's a common one. Right? Um, the, um, I did return your potential dynamics quiz. Oh no, didn't I give this to you guys the other day? Yeah. Okay. So you guys have those. You guys can do quick corrections, whatever. All right, so we're trying to figure out is what equation is going to govern the motion of a pendulum. So I got this mass, maybe so one of these guys, I put on a string. Okay, the string has very tiny mass compared to any of these. Okay? But that's part of what makes this work. Okay, pull up some angle, let it go, it's going to swing back and forth. Okay. Now, if I change this mass, well, maybe that changes how it moves, right? What if I change this angle? What if I make the string longer or shorter? Right? Also, what if I put this in a different gravity field? Now, gravity field we can't really test for in this class because we're locked in all the same gravity field. Right? But if we could, maybe we want to test that too. Right? But anyway, yesterday we narrowed it down to these four variables that we're juggling. How much time it takes to swing back and forth might have something to do with maybe the starting angle, the mass of the bob, and the length of the string. Right? I think I had you guys hypothesize, like, oh, if I change any one of these three potential independent variables, how could that possibly affect the time period? We came up with some hypotheses. But then you guys had to run three separate experiments. Okay? So, because if the theta, the m, and the l are potential independent variables, then couldn't each experiment have one of those exactly as an independent variable and the other two could be controls? Okay. So for example, if you were changing out the length every time, you'd want to control the mass, have the mass the same all the way down, and also have the starting angle the same all the way down. Okay. This second experiment, maybe you change the mass every time. But if you do that, you lock in place the length and also the angle. Those would be locked in place. And then maybe the third experiment, you change the angle by like 5 degrees every time. But if you do that, you lock the mass and the length in place. Right? And those could be controlled. Okay? And by doing that, we can get one, two, three different perspectives. And our goal is to push this all together into one giant master formula. Okay? And of course, I have a textbook answer to this question. And last class, this worked out really, really good. Like they got it right to the like within 1%. So man, let's see for you guys. We're gonna find out. So first graph we're gonna do. Right, you guys have your tables out. Have somebody volunteer their data. Let's do time period and seconds as a function of angle and degrees. Now, if there's some significant relationship here, I would either change that angle to radians or put it inside a sine or a cosine. But let's just plot the points for this first, see what it looks like, and then we'll figure out where to go from there. All right, so who has some pretty good data they can volunteer? Oh, Gian, you're volunteering. So what was the biggest angle you guys used?
Okay, the biggest angle was 70.
70 degrees. All right, so guys, let's scale this up to 70 degrees. Let's go 0, 10, 20, 30, 40, 50, 60, 70. There we go. And 20, 30, 40, 50, 60, 70. Yeah, 70 degrees. All right, from the vertical. And what was the longest time period you guys had?
Oh,
Let's not check that, but you want to do that.
Tell you what, guys, if you haven't done the graphs yet, just go ahead and copy what I'm doing. If you already did the graphs based on your own data yesterday, then that's okay. You can keep what you have. Right? But otherwise, yeah, you can just follow this. Yeah. So your biggest time period was what?
it was so for 70, it was uh 9 seconds and for 10 or for one.
Just for one cycle.
Oh, just for one, it was 0.966.
Okay. So just tiny bit less than 1 second. So let's go. How about a quarter second, half a second, 3/4, 1, and like 1.25. I think that should contain all the data here. So 0.25 seconds, 0.5 seconds, 0.75 seconds, 1 second. And you said at 70 degrees it was like 0.9 something?
Yeah, 4.966.
Right. So it could be like right here. Bam. Yeah, 0.96. Yeah. So almost 1 second. Okay. And of course that also corresponds to a specific angle and mass amount, but those are controls. Okay. All right. What's another coordinate?
So So for 60, we got 0.925.
Ooh, 0.925. It's a tiny bit less, but not much. Okay. Almost the same.
And then we got for 50 that 0.922.
22. Bam.
And then 40 is 0.909.
909. Bam.
And then the same, we got the same thing for 30.
30. Bam.
And then for 20, you got like, I'm just gonna say like 0.94.
0.94.
Oh no, 0.904.
Oh, 904. Oh, okay. Okay. So it's somewhere here. Okay.
And then then after that for 10, like 0.01.
Huh?
0.
Oh,
0.90.
Oh, 0.901.
Yeah.
All right. Okay. All right. Okay. So, where's here it is. So guys, look at those dots. Actually, that's pretty good data right there. Okay. Which basic relationship do you think that's going to fall into?
No relationship?
Yeah, no relationship. No relationship. Okay, so turns out that weirdly enough, it doesn't matter what angle you pull the pendulum to from the vertical. It takes the same time regardless. Huh? It's a shallow angle, maybe it's just right moving kind of slowly, or a large angle, it looks more quickly. Like the speed, max speed could change, but the total time to cycle once is independent of the angle you pull it from. Yeah. Okay. Now, some textbooks say, well, if you want to get strict about pendulums, really you don't want to make the angle go much above 30 degrees or so. So that's the thing too. Also, you guys, did you guys notice there's a tiny, tiny upslope to this? A tiny upslope? Or wait, never mind. Sorry, I'm thinking of something different. Okay. That looks okay though, right? That's pretty good.
Yeah.
Okay. So I think by the time we come up with some master equation to govern how's the pendulum going to swing, angle is not even going to be part of the equation because it doesn't matter. So let's go on to mass. Let's say time in seconds as a function of the mass that you hump here, the mass at the bottom. Okay. Who has some pretty good data for this one? How about Samuel? You got some data for this one? Different masses?
Different masses, yeah.
Yeah. What's the biggest mass you use?
The biggest mass we used was 70 grams.
70 grams.
Oh yeah.
All right. So okay. So let's go ahead and just put this in grams. Okay. Because really, I'm just looking for proportional relationships right now. And scale this up to 70. Just go. Oh, hey, it's the same scale as before. 10, 20, 30, 40, 50, 60, 70. 0, 20, 30, 40, 50, 60, 70. All right. And what was the longest time period you guys had?
2
2 seconds?
2 seconds.
All right. So go 1, 2. So 0, 1, 2. Yeah. All right. Let's get some coordinates. What's one coordinate?
It's all 2.
It's all 2?
Yeah,
I think the calculator was
All right.
rounding straight.
Did you do like a?
I like
Yeah,
we did a division by 3 for our period. No,
Oh, okay.
and I think our calculator was just rounding all the way to 2 every time.
Okay. So you're saying you also got a flat line? Okay.
Yeah.
Yeah, you try all these ways like 10 grams, 20 grams, 30. Okay. Yeah, so try all these grams, 10 grams at a time, all the way up to 70. You're just getting 2 seconds, regardless of the mass you were hanging on. Okay. Hey, is that kind of the same story as before?
Yeah.
Okay. Yeah. Which is that it looks like there's also no relationship between these two. Right. So again, by the time we come up with some master equation to govern how much time does it take for a pendulum to spin back and forth, the mass of the bob is not going to show up in the equation either. Right? Doesn't matter. Right? So light, heavy, right? Which may reason, I forget what you hypothesized yesterday, or maybe it's different hypotheses, right? But I'll tell you a story that's consistent with that I've been telling you guys all year. You guys remember the Galileo experiment? It runs to the top of the Leaning Tower of Pisa and drops these two objects off? Okay? And they fell together and hit the ground at the same time the whole time. Okay. Well, no, I know the bigger one here in my left hand is heavier. It has more force acting on it, but it also has more mass, more inertia. Those two effects cancel out. It's kind of physics quantum explanation. Okay? That's why they might follow the same gravity field. Okay? But if you just hook each of these to strings, right, and let it swing back and forth, I think they could also swing side by side. Right? And that's also an interpretation of this graph right here. Okay. Okay. All right, so third variable, length. So let's go time and seconds as a function of length. That's some pretty good length data. How about Kai? Did you switch out the links?
No, that was the last one.
Diego? Anna, do you have link data? All right. What was the longest link you guys used?
70 centimeters.
70 centimeters. Everybody's going up to 70. Sure. Let's go 10, 20, 30, 40, 50, 60, 70. So this will be in centimeters, right? Actually, you know what, guys, I changed my mind. Let's switch this to meters because we're gonna work with these numbers later, and it's better to have this one in base SI units just for you guys will see. Okay, this will be helpful later. So let's call us 0, 0.1, 0.2, 0.3. All right, going all the way up, and there's 0.7. Okay. What was the longest time?
1.61.
1.61. So let's go 1, 2. So 0, 1, 2 seconds. Okay. So all these graphs, of course, are starting at 0, 0, scale linearly. Okay. All right, let's get some coordinates. What's one coordinate?
Centimeters.
0.76. Okay. Bam.
20 centimeters, 0.97 seconds.
0.97. Bam.
1.11.
Okay, 1.11. Bam.
1.26.
1.26. Bam. 1.32. Bam. 1.52. Bam. 1.61. Bam. That looks like some pretty good data. What relationship do you guys think? How many of you guys think this one right here? This root. Yeah, I like this root. I like this root right here. I think the curve, the best fit is going to go.
If we go with it, start at 1 and then start at 2. Oh, start at 0.
It's going to go basically like that. I think that's your curve best fit, right? Or at least I suspect that. But there's one more graph that we're going to make, okay? And I think it'll be more obvious after we make this last graph. Okay? But what is this last graph going to do? We're going to do a linearization trick. Okay? So if I suspect that time proportion or that time period is equal to, let's say, some constant times the square root of L, which is what I'm claiming with that square root curve. I'm claiming something like this, right? Okay. It's like, well, how curvy is this curve? Like, what k value could I attach on here to like stretch this curve and it could fit exactly? Okay, what's the k? Okay. Now, at face value, that might be kind of hard to get, okay. But there's a couple of ways that we could get it. Okay. One way is you could graph not time versus length, but time versus the square root of the length. Okay. And that should, all the points should line up in a straight line. Okay. And then once you do that, you can do this rise over this run. You get the slope that way. Okay. And then you could very simply do y equals mx, and you can figure out kind of what that k is. Okay. Alternatively, you could, guys, could I square both sides of this? Like here, right now I'm claiming time is proportional to root L. But if I square both sides, it's the time squared is proportional to just L. Okay? So I could graph that, do t squared versus L, which is a different graph, but the points would also line up in a straight line. Okay? And then I could do rise over run and get a slope this way. I mean, be like a different, so it'd be like k squared. If this is k, this is like k squared. Okay. Okay. Yeah, you could do either one of these. I'm gonna walk you guys through this second option. So t squared versus L. Okay. So we're gonna do next. Let's go t squared, and the unit's gonna be square seconds. Okay. Anna, you ready to square all these? Okay. So back over on your table, I should say this too, is we're gonna throw in one more column. Let's go t squared. The unit's gonna be square seconds. So for example, if the time period was 0.8 seconds, guess what is 0.8 squared? 0.64. Right? So it'd be 0.64 square seconds, okay, which is an abstract idea, but it's gonna make a really nice looking graph that's gonna let us make an equation. What we're gonna do. Right, so maybe I'll scale this up to like 4, because I know 2 squared is 4. So let's go 1, 2, 3, 4. So 0, 1, 2, 3, 4. Oops, this is closing structure here. Okay. I'll keep the horizontal axis the same, length in meters, and scale it also the same as before. So 0.1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7. Like that. All right, Anna, you have some values for this? All right, what's one coordinate?
0.5776.
Point. Oh, is that at 10 centimeters?
Yeah, that's
Okay, you said 0.5.
7.
776. Okay, I'm gonna label that one. So this is 0.1, 0.5776. Okay, and this is meters and square seconds. Okay, what's another point?
0.94.
0.9409. It's right up there. Okay, and 30 centimeters. 1.23 something. It's probably right about there.
1.5876.
1.58. Right up there.
74.
174. Right there.
2.31.
2.31. It's probably right about there.
2.5.
2.59. Right about there. All right, so this point is 0.7, 2.59. We got meters and square seconds. Okay. Yeah, guys, does that look like it linearizes a lot better? I could take my ruler and just zip a straight line through this. Yeah, it goes right through the origin. That's really nice looking. Yeah, yeah. Okay. All right. So let's find the slope of this line and then we'll figure out what from there we're gonna do. So it's slope. I can do rise over run between these two coordinates. Okay. What's this rise over this run here? Change in time squared over change in L. Right, Patrick? So, this paper here. Where's your time? So I'll say the slope of that line that you're looking at is the change in t squared over the change in length, which is like 2.59 minus 0.5776. That's square seconds. And the run is 0.7 minus 0.1, and that would be meters. Yeah, so I just took these two coordinates, change of y over change in x. Like I said, you guys look. Okay. See what number this is. So 259 minus 0.577 over 6. Okay. I'm looking at 3.35 something. That's square seconds per meter. Okay, so then I can make an equation. Now, my y-axis is really t squared. My x-axis is the length. Is that? Okay. So I can say that t squared is equal to, now we're going to have an exact equation. 3.35 something square seconds per meter. Okay. And then multiplied by the length. Okay. Now that's perfectly valid. Okay. Or if I just wanted to simply solve for the time period, well, guys, what do I have to do to this equation to solve for t? Yeah, square root. I saw it do square root. I'm getting 1.83 something. That would be seconds per root meter times L. Okay. Okay. Is it? Now, what all is involved in this number, this 1.83 number? Okay. Do you guys think that Earth gravity has something to do with this number? Like, if you did this experiment on the moon, I think the pendulum would swing differently. Yeah. So Earth gravity is somehow embedded in this number, has something to do with that. Does the mass of the pendulum matter? No. Does the angle matter? No. Okay. So whatever. Oh, whoops, I forgot one thing. What did I forget? Yeah, square root of L. Oops, there you go. Okay. So now, as long as you're at the surface of Earth, you can tell me the length of your pendulum. You say, oh, I have a pendulum that it's really long. It's like 3.5 meters long. Say, okay, take 3.5 meters, put it here, take square root, multiply by this magic number, and I'll tell you how much time it's going to take to swing back and forth. Is that? You guys ready for the textbook answer? And we're going to see how close you guys are. I bet it's going to be pretty good. So here's straight out of any physics textbook. So the time to swing back and forth is 2 pi square root L over G, where L is the length. There's gravity field of the planet. Okay? Notice, just like you guys found, that m and the theta are not part of this expression. Ooh, Okay. So let's look at that. Let's compare to what you guys got. Let's talk about that here. Oh, yeah.
I never finished the information of the last graph. What I need
Uh-huh.
to fill it out.
No, just whatever you got. It's okay. Yeah.
Okay.
So you got. All right. So, if the actual textbook answer is 2 pi, time is 2 pi root L over G. Okay. And I want to make it look more like this answer I boxed in from your guys' lab data. I can do this. Time equals 2 pi divided by root G. This is all times root L. Okay, is that the same thing? Okay. So here's straight off my poster, and then I can just shuffle this around a little bit. Okay. And oh, look at this right here. It's 2 pi. Is that a constant? That's a constant. And gravity field, well, we are locked into a constant gravity field, so we'll treat that as a constant too. Okay. Oh, guys, in fact, if I plug in Earth gravity for that G right there, what should this bit be that I circled? What should that come out to? It's on the screen somewhere. Exactly, 1.83. Should this be 1.83? All right, let's find out. Let's see how close you guys are. Take 2 pi, all right, divided by square root. Let's go 9.8 for 9.8 meters per second squared. That, by the way, why I wanted to use length in meters so that I can put in 9.8 right here and there's no problems. Okay. Let's see. Ooh, 2.0 something. That's pretty close to 1.83. Like 18, 20. Yeah. Really good. Really good. Okay. There you go. Okay, you guys go with the pendulum? All right. All right. So you guys have all your graphs done. Yeah. All right. There you go. All right. And it all led to this right here. And so I'm going to take a few minutes to go through these posters. These are always like classic physics 1 questions. I just turned to poster form. I'll show you guys how to navigate around here. Okay. All right. Here, guys, let's do some proportions while we're looking at this. Okay. What if you have 2 pendulums side by side? Let's put them in the same gravity field. But what if the length of one is 9 times the other? Like one's 10 centimeters, the other's 90 centimeters. So 9 times the length. Because if you have 9 times the length, how many times the time is going to take to swing back and forth? What's this? Yeah, 3 times. Because that's the square root of 9. Square root of 9 is 3. It's that. That's like a proportion. Okay? You can play any exact values you want. Make this 10 centimeters, go to 90 centimeters, okay? Whatever gravity field. Okay? It's going to be like 3 times the time. The square root of 9 is 3. Okay? What about this? Okay? What if you went to the moon? I'm going to focus this a little bit. Let's say you went to a really tiny moon that had 1/9 of the gravity of the planet. Or moon actually has 1/6, but I'm going to go even smaller. Guys, what if the gravity field's 1/9? Would it take more time to swing back and forth in a very weak gravity field? Yeah, I think it would. How many times the time? 3 times, right? Because 1/9, and then take the square root. That works out to 3. Yeah, 3 times the time. Yeah. Okay. All right, here's the pretty close lab table you guys had. Got that. Okay. Oh, here's all the graphs. Right, we just made all 4 of those graphs, didn't we? You guys got those. Ooh, here's a fun one. All right, so stretch your guys' imagination a little bit. What if you have a clothes hanger and you put that on a doorknob and you give it a little bump? It starts oscillating back and forth. Right? Well, this does not look exactly like the classic bob on a lightweight string. So how much time does it take? Okay. So the form is a little more complicated, right? But guys, what do you think this I stands for? Yeah, rotational inertia. Rotational inertia. Okay. So what I do want you guys to see is the connection between this more general type pendulum and this classic pendulum. Okay? Because what do you guys know about rotational inertia of a point mass? Let's go back a couple of weeks in this class. A point mass, what's the rotational inertia?
0.
Something squared.
Mass.
M R squared, mr squared. You guys remember mr squared for a point mass? Okay. In this case, the r is actually the L, isn't it? Okay. So in place of this I, can I just do ml squared, and then I can solve this for a classic pendulum? All right, let's try that. See what happens. So if I do time period for a classic pendulum is 2 pi times the square root of, in place of rotational inertia for a point mass, I'll put ml squared. This is mgl. Okay. Ah, now what happens? And it was t equals, okay, I got the 2 pi, I got a big old square root, I got a fraction. Up here I just have 1L, and here I just have the G. Hey! Look who it is! Oh yeah! Classic tension. Same thing you got for your lab. Same thing.
So that equation will work for.
This only works for the classic pendulum that you guys did yesterday. Right? If you have like all the mass is basically this point mass here, and the string is very, very lightweight in comparison. Right? What I sort of derived this from this perspective is like in general, if you have some very complicated thing shaking back and forth, right? That's not a point mass. You can put I here, right? They did simplify to the same thing.
Okay.
Yeah. All right. Another oscillating scenario you guys are going to see in the next couple weeks is like a mass on a spring. Right? So I do have a lab queued up for this, so I'm kind of spoiling some answers, but that's okay. So what if I hang a mass on a spring? Guys, what does K stand for? Spring constant. Spring constant. You guys remember like how stiff these springs are? You guys remember your lab scales? These are like hundreds of newtons per meter. Right, you guys remember that? Okay, so how stiff is the spring? Right. And then I pull this down a little bit, let it go. You're boing, warning, or warning, or warning. How much time does it take to do that? Right. Well, if you do a little side by side, this actually is a pretty similar looking expression, isn't it? Okay, looks like it. So here's the pendulum, here's the block on the spring. Time period is got 2 pi, got a square root, got a fraction. But then what's inside the fraction is a little different. L over G, M over K. Is that? I think that makes sense. All right, well, part by part. Because here, guys, imagine this versus this on the same stiff spring. Okay. Guys, what makes more sense? If this is going like could this be like bow or does that make sense? You guys think? Of course, you guys get your hands on these materials pretty soon, so you'll see that too. Okay. So I'm claiming if you increase the mass, you're going to increase the time period. Right? Ah, I think that makes sense. Okay. And what if you have a spring and you make it stiffer and stiffer and stiffer? Like a very loose spring might be like, and a very tight spring like, so if you increase that K, you decrease the time period. Okay. Guys, what about this? What if you have this on Earth, right? You attach the slab weight, you let it go and oscillates on Earth. Okay. Let's say it takes 1 second. Right? From the top back to the top takes 1 second. You guys got that? What if I took this to the moon? Took this to the moon. Would it still take 1 second, more than 1 second, or less than 1 second? Let me see, show of hands. So you guys know the 3 options? All right, so here, I'm going to repeat that. Okay, so everybody listening? Okay. So I do this on Earth. I hold this here, I let it go. Let's say it takes 1 second to cycle back and forth once. Now I'm going to take this whole thing to the moon. On the moon, is it still the exact same 1 second? Is it more than 1 second, like super slowed down? Right? Or is it less than a second? Like, right? On the moon. Who says it's going to be more than 1 second? And this thing's going really slow. Who thinks it's less than 1 second? It's back really fast. Right? Who thinks that on the moon is the exact same as it is on Earth? Yes. How do you know?
Gravity's not involved in the equation.
Yeah, because gravity's not in the equation. Only the M and the K. But, yeah, gravity still doesn't matter. Yeah. Right. So eventually you get a lab table that's fairly similar to that. Right. Okay, and eventually come up with some graphs that, well, these could be some graphs you guys are gonna make. Ooh, this is a funny looking graph down here. Got something sinusoidal. Yeah, like height is a function of time or position versus time. It's a warning. It's gonna oscillate. All right. Here's a good abstract one. This is gonna lead into we're gonna start setting up some graphs with you guys here. This oscillating graphs, okay, but it's gonna lead to what if I have a vertically hanging spring oscillating from this lower point to this high point? It's going you guys think its speed is constantly changing? Right? Well, guys, where do you think it's going the fastest? At the bottom, middle, or the top? Where's it going the fastest? According to radar gun head. Actually, where it's turning around, do you think it has 0 speed? Where it's turning around?
Yeah.
And how about through the equilibrium point? Be going the fastest, wouldn't it? Fastest speed. I think it has the greatest speed right in the center, and it has greatest acceleration at the end points because it's turning around. Ooh. Right? But what if I turn that whole thing horizontal? Now, could you guys imagine if there's an air hockey table? You guys see an air hockey table right here? Okay. and I pull this back and let it go. Oscillates just horizontally with no friction. Okay. Do you think it's also going the fastest through the center? Fastest through the center? Yeah, like that. Okay. Okay. So now what we're gonna do is we're gonna take the horizontal one and treat this like east-west. Take the vertical one, treat this like north-south. It's gonna map coordinates. Coordinates of what? Well, let's get up in a helicopter and look straight down at that car on that circular track. And this car is going around a circular track, just constant speed. He's always turning left, but he's going at constant speed. You guys see that? Okay. And it turns out that this east-west location can be exactly described by this mass on this spring. And the north-south location of the car can be exactly described by this vertical type spring right here. So this the circle is sometimes called phase space, right? If you Google that, I bring something out of that. Okay. So that's an interesting context for this. Again, it's all leading up to these graphs like sine and cosine we're about to get to. Okay. Now I do want to introduce some other ideas before we look at those graphs. Okay. So guys, let's talk about frequency and time period. So frequency is just the reciprocal of time period. Well, vice versa. If something's the reciprocal of something else, they have to be reciprocals of each other. So let's do some numerical examples. Okay. Like, guys, suppose you have a pendulum. Okay, let's do a pendulum. Okay. And it swings back and forth in a half of a second. You get it? Like zoom, 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 zoom. Takes a half a second to cycle. Okay? Now if that's true, how many cycles is it doing every second? Here, guys, I'll say it again. Oh, you're saying two? Yeah. Yes, yeah. If it takes half a second to go from the left side back to the left side, right? Then if it does that twice, that would take a second. Okay? Another way to say that is the frequency is equal to 2 hertz. This is hertz. Hertz. S, of course, is seconds. Seconds. Okay. Hey, what about this? What if I have a different pendulum? Let's say it's really, really short. Okay. And it's so short that it only takes a tenth of a second to swing back and forth. It takes a tenth of a second. Okay. In 1 second, how many times would it swing back and forth? 10. So now the frequency could be 10 hertz. Is that okay? Okay. And what I'm trying to show you guys is a numerical example of these guys right here. Okay, so frequency and time period are reciprocals. Okay, and frequency is in hertz now. Okay. Now there's a special kind of frequency called angular frequency, which is going to be really helpful for the graphs we're about. Oh, here's a couple of oscillating scenarios. Got a pendulum, got a mouse on a spring. Okay. So if you take that frequency and you multiply by 2 pi, that creates something called an angular frequency. Now I know we've been using this omega for angular velocity the last few weeks, but that's not the case for this one. This is called angular frequency. Okay. And the reason it's going to be helpful, but the best explanation I have is the unit circle. Do you guys remember? Do you guys learn the unit circle in math? Okay, let's do a quick review of the unit circle. So if you're going around the circle, let's start here at 0 radians, which is 0 degrees. Okay. And so if you go halfway around the circle, call that 180 degrees. Right? How many radians is that? Pi. That's pi radians. Right? If you keep going all the way to 360 degrees, that's equal to what?
2 pi.
Yeah, 2 pi radians. Yeah, 2 pi. Okay. Now we're gonna work in radians here. Right, because we're going to directly multiply angles, you have to be in radians. Okay? So I see that every time I hit another 2 pi radians, I made one complete cycle. Okay? So how can I describe either the height position of this block on the spring, or maybe the horizontal position of this bob, sort of like that, right? With like sine and cosine? Because it is oscillating, so sine and cosine would be good choices. Okay? Okay, so I'll do it this way. I'll say x, again, either x this way or x this way. Okay? I'm going to start with a cosine, and then omega t, where omega again is this angular frequency, 2 pi f. Okay? So for example, if it took a tenth of a second to cycle once, that I think the frequency would be 10 hertz. Do you guys see that? Okay. And then if you multiply here, guys, if you take this 2 pi f and sub it into this omega right here, what is 1/10 times 10? 1. And then you're left over with this 2 pi. And what's cosine of 2 pi? Well, that means you cycled all the way around once, because cosine of 0 is 1, cosine of 2 pi is also 1, right? Okay, so that means you've gone from here to here. And that, you guys can see it visually. You guys see that's one complete cycle? You see it? Ah, okay. Now, what do you guys think this A stands for? It's a word that starts with A.
Amplitude.
Amplitude. Okay, guys, could that be this height from the x-axis, or the time axis to the maximum point? It could be this amplitude right here. See that? Okay. Now, I usually start these equations off with cosine because cosine of 0 is 1. So if I pull this back and I start it from here, okay, now it's already displaced. So then it starts oscillating. It's like, you guys, yeah. Now, if you know position versus time, you can get velocity versus time and acceleration versus time. Hey, look, it's like the three kinematic type graphs, right? X versus t, v versus t, a versus t, right? Is anybody here taking calculus? Anybody take calculus? Oh, okay. A few of you guys are. Okay. If you're not, don't, you're okay. But if you are, there's a calculus connection here. Guys, what's the derivative of cosine? Let's just say the rate change of cosine. Isn't it like negative sine? Hey, that looks like this right here, negative sine. And what's the derivative of sine? It's cosine, right? And if it was negative before, now we're going to keep the negative, right? So cosine to sine, we change from positive to negative, but sine to cosine, you just keep the same sign as before, right? One more detail. So I have this angular frequency in here, but look, it gets pulled out here as omega, and then it looks like every time I take another rate change, calculus is called a derivative, right? It looks like another omega comes out, another angular frequency, right? And that's called the what rule in calculus. Starts with a CH. You guys know the chain rule? Chain rule? Yeah. Oh no. Oh, okay. All right. Anyway. But you guys have here. Hold on. Here, we'll do a little side thought. Okay. Guys, what if f of x is equal to let's say 3x here, let's square the whole thing. Let's do 3x quantity squared, which is equal to, of course, 9 times x squared. Okay. Let's say we take the derivative. Let's do f prime. We're doing a little calculus here. Okay. Now this one, can you just pull the 2 down and say 18x? Right? That's the rate change of this parabola as the straight line. Okay. Or alternately, can I take this 2 and pull it in front and do 2 times 3x to the 1? But then I have to do chain rule. So I have to say times 3. Okay. And put it all together. Guys, what's 2 times 3 times 3? 18, which is the same thing as this over here. Okay, you guys see? All right, so that's a little chain rule. All right, well, that's about as far as I'm gonna get my earlier classes. Again, my AP classes had some extra things to do, so I'm gonna finish off class with you guys get to watch Blackburn Pendulum. Oh, just turn in your labs. It's got your name on your labs? All right. All right, we'll check out some Blackburn Pendulums and close the class.